everyone, welcome to Computer Day. Today we learn about Banker's algorithm. It's a deadlock avoidance algorithm. Banker's algorithm, the name chosen because this algorithm may use in banking system to ensure that the bank never allocated its available cash in a way that it could no longer satisfy the needs of its all customers. So let's take an example and understand the algorithm. Consider a system with 5 processes: P0, P1, P2, P3 and P4. Okay, and there are 3 resources. Suppose A, B and C resources may be CPU, it may be memory, or suppose printer. Okay, now suppose this is a scenario of the system at T0 time. Okay, and there is 5 processes. What is the allocation? Allocation means the number of resources, or we can say the instance of the resources allocated to the process. Suppose this is a allocation of resources of P0 process. This is for P1 process. In this way, allocation means the current allocation or currently allocated resources to this process. Okay, now it is the total number of instance of the resources A, B and C, that is 10, 5 and 7. Now what is the maximum need? When a new process enters into system, it declares the maximum number of instance of a resource, that is A, B or C here, and it is declared the maximum need of the resource to execute the process. Okay, now Banker's algorithm determines whether the allocation of the resource or this resource allocation of the system is safe or not. It is in safe state. Safe state means, suppose here we written safe. Safe state means where deadlock not occur. Deadlock not occur. This is safe state. And when it is an unsafe state, when deadlock occur. So this algorithm determines this. And if the system is in safe state, means deadlock not occur, so we find this. Now to find the available resources, we have to find what is the total resource and what is the resource that already allocated to the processes. So we can find the total allocated resource. To add this, for C is a resource and total number of instance is 5, what is already allocated. For B it is 2, and for A it is 3 plus 2 plus 2, that is 7. That means that this instance of this resources are already allocated to the process. Okay, now this is already allocated and this is the total number of instance of this resource. So what is available? Total minus allocation. If we find that, we can easily get the available resources. So 10 minus 7 for the resource A, that is 3, this is available. And for the resource B, 5 is total and 2 is already allocated to the processes, then 3 is available. And for C, 7 minus 5, that is 2. So this is the available instance of the resources which is available. Now we have to find the remaining need. What is the remaining need? Remaining need means what is the number of instance of the resources is remaining or needed or requested by the process to execute it. So this means this is the maximum need and this is already allocated. So what is the current need, means remaining need, and how we find it? Maximum need minus allocation or allocated resources. So we find in this way. Here 7 is the maximum need to execute the process P0 for the resource A, and no instance of the resource A is allocated. So need is 7. For B, 5 is needed and 1 is allocated. So remaining need is 4. And here for C, 3 is needed and no instance is allocated yet. So need is 3. In this way, we can find all the remaining need for process P1, P2, P3 and P4. This is here 2 minus 0, that is 2, 2 minus 0, that is 2, and 3 minus 2, that is 1. In this way we can find all the remaining need for the process P2, P3 and P4. Okay, this is the remaining need of P1, P2, P3, P0, P1, P2, P3 and P4. Okay, now we have to find, or now we have to decide whether the request or the remaining need is granted or not. That means if we have the available instance of the resource, that is 332, and remaining need of this processes is this. So if the remaining need is less than equal to available resources, then only the process is executed. That means if remaining need is more than available, how can we allocate the resources? We can only allocate the resources when remaining need is less than or equal to the available. So we can allocate or grant it, and then only the process is executed. Okay, so here we consider the first process, that is P0. For P0, the remaining need is 7, 4 and 3 for the resources A, B and C, but the allocated resource or available resources are 3 and 3 and 2. So we can't consider or we can't grant this request. Okay, so it is waiting until other process release some enough resources to execute this. So it is now in a wait. Now we consider P1. For P1, the remaining need is 1, 2 and 2 for the resources A, B, C, and available is 3, 3, 2. It is more than the remaining. That means needed is 1. One instance of the process A is needed and 3 is available. So it is granted. For B, 2 is needed, 3 is available. So it is also granted. And here for C, 2 is needed and 2 is available. So this is now executed. Now we introduce a new term, that is save sequence. And what is the save sequence? That means how we sequence all the processes that the system in safe state, that means deadlock not occur. How we sequence the processes that deadlock not occur. So we at first in this sequence P1 is executed without occurring deadlock. Okay, after P1 is processed, then any of the processes, after execution of any process, it releases all its resources. So after P1 execute, it release this resources. That means this is added to available resource that is available now. So we add 2 0 0 and now the available resource is 5, 3 and 2. Okay. Now we consider the next process, that is P2, but here need is 6 for the resource A and there is available of instance of A is 5, so we can't consider this. Okay. The next process is P3, and for P3 we can easily understand the remaining need is less than available, because this is available and this is the need, we can easily granted it. So P3 is the process which is in the next of safe sequence. Okay, so it is executed, and after execution of P3 it releases this resources and it is added to our available resources. So 2 1 1 is added, and now the available resources is 7 4 and 3. 2 1 1 7 4 and 3. Okay, now we consider next process, that is P4, and P4, the need of P4 is 4 3 and 3, and this is available, or we can say remaining need is less than available resources, so it is also granted. So P4 is the process in the sequence, and it P4 release its resources after execution. So 0 0 2 is also available now. So current available resources is 7 4 and 5. Now we consider all the processes, at least one. Next we also come to P0 again, and now for P0 the need is 7 4 3 and available processes are 7 4 and 5. So P0 is executed easily now because it get its resources. So P0 executed, and after P0 is executed, it releases its resources and it is added to the available resources. So it is 7 5 5 now. Next is P2. Now the need is 600 and the available resources or available instance of the resources is 755. So P2 is now executed, and after release its resource, the total available, now the available resources are 7 5 and 7 10 5 and 7. Now the available resource are equal to total resource. That means all after execution of all the processes, all the resource are free. Okay. Now, so here we find a safe sequence through this Banker's algorithm. Now, a most important thing is that there is more than one sequence. We can find more than one safe sequence through this algorithm. Okay. And now consider another situation of the system where we claim the system is deadlocked when the available resource is not sufficient, okay, to fulfill the request of the process. That means if the remaining need is more than the available resources. Suppose a situation occur where available resource is less than the remaining need of all the processes. That means we can't fulfill or grant any need of remaining processes. There only we can say deadlock occur. Okay, so hope you understand Banker's algorithm. Thank you everyone.